Hi, Les West here. This video is to introduce you to the mathematical subject of the laws of indices. I'll explain what this means and then I'll show you examples of how these laws apply. So let me begin by clarifying the meaning of this word indices. You're probably familiar with an expression written in this format, where an unknown value a is raised to the power n. Now a mathematician would call our unknown number a the base, and the power to which that number is raised, n, is called the index. But in maths, the word index means the same as the word power, or you may even see it called the exponent. And the word indices, which is our subject today, is simply the plural of the word index. So when we refer to the laws of indices, we're simply talking about the rules which apply when you're working with indices or powers. Now, before we get into this subject, you may be wondering how all this relates to real life. Well, of course, I don't know what career you'd like to follow in the future, but here are a few examples of people who would have to use indices in their professional lives. Engineers, electrical engineers, mechanical engineers, civil engineers, structural engineers. Engineers use the laws of indices when they're calculating complex designs, such as piping systems, bridges, industrial machinery, electrical circuits, electronic devices, or buildings. Accountants use the laws of indices in calculations of compound interest. If you want to know how long it will take to pay off a mortgage or the best place to invest your money, the accountant will work this out using formulae involving numbers raised to a variable power. Organisers of large sporting events, such as tennis or soccer championships, would have to use formulae involving indices to calculate the numbers of matches to be played to reach the finals and the scheduling of these matches. A medical specialist, dealing with the analysis of disease and trying to determine the rate at which the disease spreads, will use formulae based on the laws of indices to calculate where and when preventive measures such as vaccines need to be applied. Psephologist, there's an interesting word. A psephologist is the person who calculates the likely outcomes of elections. To do this, they use complex formulae taking into account the many variables of regional issues and voter needs and preferences. Computer coding uses a binary system of calculation based on the laws of indices. Computer games designers use complex algorithms to build the games so that they work precisely in all phases of the game. And scientists working in astrophysics or space exploration use the laws of indices in their calculations to expand our knowledge of the universe and to define exactly when a space launch needs to occur and what speeds and controls need to be applied to ensure a safe journey, landing and return for the astronauts. And even major sales groups like Coles or Woolworths or Amazon need people with the knowledge of maths calculations using the laws of indices to ensure that their stocks meet the likely demand for their products. These are just a few examples, but they demonstrate that complex maths calculations are needed in many aspects of life and work. So now let's consider what exactly are these rules called the laws of indices. Our first law, or rule, concerns what you do when you want to multiply two identical numbers, each raised to a different power. The example is our unknown number a, and we're to multiply a cubed by a squared. Now it seems logical that in multiplying a cubed by a squared, we would simply multiply the indices, resulting in a to the power of 6. But let's break this down. Okay, a cubed is equal to a times a times a, and a squared is equal to a times a. So if we multiply these, we get a times itself 5 times. A times a times a times a times a. And of course, that equals a to the power of 5. So instead of multiplying the indices 3 times 2, we've added them, 3 plus 2. So this gives us the first of our laws of indices. To multiply two identical base values, each raised to a power, you add the powers. Note that the bases must be identical. You can't multiply a cubed times b squared in this way. If the base numbers are different, you would have to calculate the value of each expression, a cubed and b squared, separately, and then multiply them together. So let's look at another example of multiplying base numbers raised to powers. A to the power of 5 multiplied by a cubed equals a to the power of 5 plus 3, which is a to the power of 8. To find our second law, we'll look at dividing two identical base numbers, each raised to a different power. Our example is b to the power of 5 divided by b squared. We'll start by breaking down each value. B to the power of 5 equals b times itself 5 times, and b squared equals b times b. So our example equals b times b times b times b times b over b times b. We can cancel out b times b from the top and bottom of the equation, and this will leave us with b times b times b, which is b cubed. So we haven't divided the indices, we've subtracted the second index from the first, 5 minus 2 giving us 3. And there's our second law. To divide two identical base values, each raised to a power, you subtract the powers. And another example, b to the power of 8 divided by b cubed equals b to the power of 8 minus 3 equals b to the power of 5. Okay, we've now got two laws relating to multiplication and division. So let's look at what happens when we take a base number raised to one power and raise it further to another power, as in this example, c to the power of 5 and then the result squared. Well, we can write that expression as c to the power of 5 times c to the power of 5. Now we'll apply our first rule, the one about multiplying. So we'll add the indices, giving us c to the power of 10. We've now evaluated our example to be c to the power of 10. That is, we've multiplied our powers 5 times 2 to get 10. And this gives us our third rule. To raise a value or variable presented in index form to another index, multiply the powers. And another example, c raised to the power of 5 and then cubed equals c to the power of 5 times 3, which equals c to the power of 15. Now let's look at a special case. What does it mean when we have a base number to the power of 0? Well, to take an example of how we might have got this value, look at g cubed divided by itself. Applying our second law of indices, we'll subtract the powers and get g to the power of 0. But we know that any number divided by itself must equal 1. So g cubed divided by itself equals 1. So g to the power of 0 equals 1. So the law here is that any base number raised to the power of 0 equals 1. And here are some examples. G to the power of 0 equals 1, A to the power of 0 equals 1, 3 to the power of 0 equals 1, 15 to the power of 0 equals 1, 124,000 to the power of 0 equals 1. Any number raised to the power of 0 equals 1. Well, we've done a fair amount of work so far. So now let's have a little break and we'll recap the laws we've established up to this point. Okay. The first law we established was that when we multiply two identical base values, each raised to a power, we have to add the powers. We don't multiply the powers, we add the powers. Following on from multiplying, we looked at dividing, and we came up with our second law saying that when we divide two identical base values, each raised to a power, we have to subtract the powers, not divide them. Then we looked at raising a power to another power and said that in this case we have to multiply the powers. Finally, we demonstrated that any number raised to the power of 0 is equal to 1. So now we have worked out 4 of the laws of indices. I'm afraid that the next 2 laws are a little bit more complex, so you'll have to concentrate hard as I go through these and finish off our look at the laws of indices. So the next case we'll consider is negative indices. Now, how do we get a negative index? Well, look at this example. If we apply our second law to the expression m cubed divided by m to the power of 5, we subtract the index 5 from the index 3, giving us m to negative 2. Now, we also know that we can expand this expression as shown, m times m times m divided by m times m times m times m times m, and that we can then cancel out m cubed, or m times m times m, from the top and bottom lines. And that gives us 1 over m squared. So m to the power of negative 2 equals 1 divided by m squared. So the rule for this case is going to tell us that a base number raised to a negative power is equal to 1 divided by the same base number raised to the same positive power. So m to the power of negative n is equal to 1 divided by m to the power of positive n. Now, for this rule, the mathematicians use the word reciprocal to mean a negative power. So the rule is a negative power is the reciprocal of the positive power. Now for our final rule, we're going to look at how to resolve an index expressed as a fraction, such as this example, p to the power of a half. And in this case, we'll go straight to the rule, which says the denominator of the fraction is the root of the number or letter, and the numerator is the power to which we raise the answer. So in our example, the denominator 2 is the root of p, and the numerator 1 is the power to which p is raised. Now p to the power of 1 is simply p, and the root is 2, so p to the power of a half equals the square root of p. And if we have an index where the numerator is greater than 1, we apply the same rule. So for example, if we have p to the power of 2/3, the root is 3, and the power to which p is raised is 2. So p to the power of 2/3 is equal to the cube root of p then squared. So if we had an actual number like 8, for example, 8 to the power of 2/3 equals the cube root of 8, then squared. The cube root of 8 is 2, and 2 squared is 4. So 8 to the power of 2/3 equals 4. So now we've established our 6 laws of indices. The first 4 we read out earlier, and the last 2, number 5, a negative power is the reciprocal of the positive power. And number 6, where we have an index in the form of a fraction, the denominator of the fraction is the root of the number or letter, and the numerator is the power to which we raise the answer. Well, I hope that this has given you an idea of what we mean when we talk about the laws of indices. We've gone through 6 examples, finding a new law for each case and expressing the law in words. If you remember these laws, you should be able to apply them to many mathematical problems you'll come across. I hope you'll join me for another short video soon. Goodbye for now.